Good afternoon. This is Dr. Shulman reaching out. I am going to go through a top four, which is it's basically hypothesis testing with standard deviations and variance. So we're doing chi-square. That's pretty much what we're going to do. So I'm assuming we're going to do this with p-values, critical values, as well as the confidence interval. I'll do my best to make this clear. Sorry, I lost my video for a second. So I'll do my best to make this clear. Again, always email me. I'm going to go through the textbook and then I'm going to go through as many problems as I can. So feel free to just reach out any way I can help. All right, so I'm going to share my screen. And we are here. Just grading some late work, which is totally fine. Sorry you're seeing people's grades for a second. I hope they don't mind. So if you go to modules, you'll see that we are in the last part. We are in the last part of 8. We've made it all the way through hypothesis testing up to 8.4. What does 8.4 have in store for us? 8.4 has 4 problems, 1, 8, 10, and 13. So I'm assuming there's going to be not much in here since we did this twice for the probabilities, we did it for the t-test, and now we're just going to do this for chi-squared. And once I'm finally done with all of them, I'll just make you a t-test video so you can see how t-tests are done. That's my goal. We'll see. All right, so we're just doing 1, 8, 10, and 13, 4 problems. Shouldn't be too crazy. So let's go to My Math Lab and Mastery. I'm going to go to Open My Math Lab. And I'm going to go to eText. I'm going to click the Pearson eText right here. And we got to go to 8.4. This was 8-3. I did this one last time. And here it is. So this is what we're doing today. We're going to do hypothesis testing about standard deviation variance. I've never really seen a lot of research that does this, to be perfectly honest. I think it's probably for a lot of mechanical research for standard deviation and variance. We're just like trying to figure out, okay, like how much error can I have for like a nut or a bolt? I think that's probably where these formulas are used a lot, but we'll see what examples they have. I'm also going to be writing stuff in the notes. Here's 8-4. Here's all the rest of them. If I make any mistakes, feel free to just email me. We're all human. We all make mistakes. That's how we learn. That's how I feel about it. So if I'm making mistakes, so again, I'm in Intro to Statistics 8.4, and let's make it happen. So, okay, they say it's done in business. Is to improve the quality of goods and service by reducing variation. That totally makes sense. So, if you remember the video that I have with the four dartboards, I can draw it real fast. So here's my 4 dartboards. I think this is the point they're trying to make. Here's my 4 dartboards. And basically, we're going to do the difference between, okay, so the first one I'm going to do, okay, so that's the first one. We're going to have one that looks like this. We're going to have one that looks like this. And we're going to have one that looks like this. So when they say reducing variation, to me, they're talking about reliability. And reliability means what? It means repeatable. Can you do the same thing over and over again? That's what that means. This is different from the word accurate, okay? The actual value. My favorite example of this, besides the dartboards, is like a scale. So let's say I weigh 160 pounds. I get on the scale, it's 163. Get on the scale, 161 and a half. Get on the scale, 159.50. I get off the scale, 158. The scale is accurate. It's close to my actual weight, but it's not reliable. It's not repeatable. The opposite is true. It's like, let's say I get on the scale, it says 512 pounds. I get off, get back on the scale, it says 512 pounds. I look at myself, I see like, oh my God, did I lose weight? Or I mean, like, did I eat a house or something? I get back on the scale, 512 pounds. So this is a what? It is not an accurate scale, but it's a reliable scale. So see, this one is accurate, but not reliable because it's not in the same spot. This one's accurate and reliable. This one's reliable because we're hitting the same spot with our darts, but it's not accurate. And this one is not accurate nor reliable. So that's what I think they're trying to get at here. When they're saying they want to reduce variation, they just want to make it as repeatable as possible, whatever we're getting, whether that's wait times or whatever. This section presents methods for hypothesis testing and about a population standard deviation or a population variance. So remember, this is our standard deviation for the population. And if we square that, we get the variance. Just so we remember what the formula is. So whenever we want to get the standard deviation, okay, this is what it is, your x minus your mean. So this is every data point minus the mean squared. And we have to add all of these up. That's what the sigma stands for. That's what the summation stands for. It actually looks more like this. Oh my God, I can't draw to save my life today. Usually this is the first value. This is the last value. That's what goes here. That's what goes here. And then what do we do with this whole thing? We divide it by n minus 1, and then I take the square root of it. This is for a sample. The only difference for the population, for getting this one, the only difference is if we want the population, it's just an n on the bottom. And this is minus what? This is minus the population mean. So this is for the population. Just so we can remember where these formulas come from and what they do. All right, let's see what we got. Okay, we have our notation. N is sample. S is your SD of the sample. So is your sample size. This is your population. This is your SD of your population. This is your sample variance. And this is your population variance. Now, in order to do this, and you can see this, the formulas are barely different, right? Sample, we have to minus 1 because of degrees of freedom. This, we have the whole population, so we use n. A lot of times it's using big N instead. There we go. All right, to do this, we need a simple random sample and it has to be normal. It doesn't matter how big it is. So a lot of times we're going to be using the QQ or building a histogram. So simple random sample. And what is the other piece we need for this besides the simple random sample? It's got to be normal distribution. Pretty sure that's what it's going to say. Ta-da! All right, so here's our test statistic. This is what we're going to do all the time. So here's our chi-square formula. It's n minus 1 times the standard deviation, times the variance over the population variance. That gives us our chi-squared term. So notice that in this formula, we're using the variance for both. We're not using the standard deviation to get our test statistic. We are using the variance. There's our degrees of freedom, our critical values. We'll also be using this degrees of freedom, which equals that minus 1. That's what goes there. Okay. And we have a table A-4 that I'm sure we can use. Let's look for A-4. Here's our chi-squared. Here it is. Oh yeah, remember that this one was to the right because it's a positive, it's a positive skew. So this is the chi-squared graph. So we're always going to the right because it's not normal. It's positively skewed. So let's say we want a I don't know. Let's say it was we want to be 95%, right? I would, and I wanted, and I had 11 people, so I'd be here. My critical value would be 3.94. All right, let's keep it going. Aha, there it is. I love it. Oh, I gotta blow my nose. Be right back. All right. Okay, so the chi-square distribution was introduced. We noticed that it is right or positive skew, right skewed. There's one for each degrees of freedom. The critical values are using 8, 4. Degrees of freedom for 10, degrees of freedom are 20. Okay, all that stuff makes sense. Caution, for chi-square distribution, use cumulative areas from the right, unlike the standard one, which is to the left. Okay, that makes sense to me. Let's keep this idea going. Sweet, we got a problem. I've been waiting for a problem. So, U.S. Mint specifications require that quarters manufactured after 1964 have a mean. Okay, so here's our example one. Our population mean, not our sample mean, is what? I'll do the whole thing by hand, and then I'm sure I'll figure out how to use the computer to do it. So our mean is 5.670, and our population standard deviation is 0.062. Listed below are the weights grams of a simple random sample, nice, made with a new minting process designed to reduce the standard deviation, so the weights are more consistent. We're using what? 0.05 significance level. So that's our alpha is 0.05. That means we could be 95% sure. And we have to claim that these weights are from so we have to say that it is less than that. So our null hypothesis is going to be that our standard deviation is going to be equal to 0.062. And our alternative hypothesis is what we want to prove, right? What we want to prove is that this is going to be less than 0.062. So we have this values, but we need our sample. We need a sample mean. We need a sample standard deviation. I'll just put SD here. And we also need a sample variance, I'm assuming. And we can make this variance by just doing what? Squaring this value. So we have that. We also need our n for how many things we have. So ready? 3, 6, 9, 12, 15, 18, 21, 24. I counted by threes. So we have 24. That's our n. That's the first thing we need. Our degrees of freedom is 23. These are the first two things we need, okay? We can look at the table and get our critical value already, but like this is what we have right away. So what am I going to do? I guess we can use Excel. You can use whatever you like for this, but I'm going to use Excel for this just so I could do all the pieces kind of fast. So I'm going to open a new sheet on Excel. I'm going to type these in. I know it's going to be annoying because there's a lot of them, but guess what? That's just the way the cookie crumbles, right? Oh, they're not letting me make a new sheet. Oh, okay. I don't care. So file, here we go. Bye, friend. I just ran out of pages because I did so many. So this is going to take me a little bit of time to type in, but I don't mind. I want to show you exactly how to do it. So 5.7424, 5.6803, 5.7222, 5.7328, sorry. 5.6245, The next one is 5.6619. The next one is 5.7268. Next one is 5.7985. Next one is 5.7041. Next one is 5.5938. The next one is 5.7180. 5.6528. Next one's 5.6342. The next one is 5.7299. 5.6210. 5.6839. 5.6582. What happened to this one? Oh, because it ends in a 0. Okay. 5.6582, 5.6613, 5.6651, 5.7360, 5.6484, 6484, 5.6925, 5.6546, and finally 5.6502. All right, so there's our 24, right? We need the mean of this, so I'm just gonna do equals average. Boom. We need the standard deviation of this, so I'm gonna do equals ST DEV dot S, because it is our sample. So the formula is a little different as that -1. So this is, I'm just gonna write sample mean, sample standard deviation, sample variance. So to get this, all I have to do is multiply this times itself. All right, and now I need the population mean, just so I have everything here. Population SD, population variance. So they're giving me these, right? They already give me these. So they already gave me these, which is nice. Now we're just gonna let the formula kind of be our friend. So our population mean is 5.670. Our standard deviation is 0.062. Our populated variance is this squared, so it's this times itself. So these are all of our values. I just want there's more than we need, but I just like getting everything. So 5.724, well, 25. The standard deviation of the sample is 0.2033. This is 0.0413. And this one's going to be 0.041341. Okay, so we've got pretty much everything we need. We have all the numbers we need. All we have to do is put it into this formula, and then we're good to go. So to get this chi-squared, all I have to do is take n-1. I use a different color. So n-1. Well, we have 24 minus 1. We need the variance of the sample, which we just got. 0.041341. And then I just have to divide it by what? I just have to divide it by the variance of the, that was the sample, the variance of the population. So it's 0.003844. This is going to give us that statistic, our chi-squared statistic. So I'm just going to do equals parentheses 23, right? 23 times what? This value, the 0.041. And I'm just going to divide it by how much? This variance. So this is our chi-squared statistic. I got 247. 247.0 0.36. Let's see if this is right before we look up the other numbers. Oh, I forgot to do all the requirement checks. Oh, no, 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 no. Okay, so we have to make sure that this is right. And my test statistic is wrong. So I made some mistakes. So let's see where the errors were. 24.04 times that 0.062 squared. Yeah, that's right. I got all the data right. Did I type it in wrong? Just so I could see it. 0.062 times itself. That's the bottom. 0.04, sorry, 0.20 times itself. That's the top. Oh, they got 0.04. They got a different, oh no, we have it. Did I use the wrong value? I got 0.02 when I put this in, so I could have made a mistake somewhere. I'm gonna do it by hand. I'll do the whole thing again. They say that the standard deviation is 0.04. We got this. We got 0.02 for our sample standard deviation. I might have typed one of them in wrong, like a fool. That's so annoying. All right, let's look at them. Well, I had to do the normality checks first, so I might as well do that. You just make sure everything looks good. 5.7424, 5.6803, 5.7222, 5.7328, 5.6245, 5.6619, 5.7268, 5.7985, 5.7041, 5.5938, 5.718. Oh, there it is. That should be a 5. 5.6528. Did it already change? Let's see. 13.79. Is that what they wanted? Yeah, one number off. Just one number and it messed up the whole thing. Why did it automatically change? Because I have the formulas here. Okay, so we got the critical value right. But you should always be putting this in the StatCrunch and checking. And that's what we're going to do. So I want to make sure this is normally distributed. So the first thing I'm going to do is I want to make a histogram. The histogram, I'm going to start with 5. I'm going to make my width 0.05. I think that's a good thing. Let's check it out. It looks pretty normally distributed. If I started at 5.4, I think it'll look better. If I start at 5.5, I guess it'll look even better. Yeah. Okay, this looks pretty normally distributed. All right, let's do the QQ sort. It's pretty close to a straight line. These all look pretty normally distributed. I'll take them both. These look good to me. If you want to just do this, you could do summary stats, columns. And if I just click compute, oops, it's going to give me all that stuff. So notice that the sample mean 5.683 we got, the variance 0.002 we got, the standard deviation 0.048 we got. So you could do that instead. So we already have all this information, right? They want us to go to the chart and look up this, and we just have to make sure it's what? Beyond the 13. I'm just glad we got the same value. So let's look at the chart. We have our null and alternative hypothesis, which looks good. All right, now they're telling us that the p-value is 0.0674. Let's double check that, right? Let's double check that. We have a degrees of freedom of 23, right? 23, one less. And we just got to get this p-value so they're saying the p-value is going to be 0.0674. So let's actually see it, right? Sorry, they say the critical value is 13.091. Let's make sure that's true. My bad. 13.091. I want to do the critical value first. Let's go to the chart. Which is tables and formulas. All right, they say it's 13.091. Let's actually see what this is supposed to be. We're at 23. 23 across. So I gotta move my floating head. 23 across. There's the 13.091. Is this in the right part? Yep, 95%. Perfect, beautiful. 95%. We got the 13.091. And now all we have to do is draw ourselves a pretty picture. And you will see why this works. I'm sure that there's going to be a computer program that does this for us. But in the meantime, we know this is how the picture looks. We want to be this way, right? So at 95%, it was 13.091. We want to be in here. So we want to be beyond that. So it could be 95% short, and we got our value was 13.79508, which is bigger. I believe that means we're good to go. Let's look at it. Okay, we're testing the claim that this is it. We have to be, the critical value is this. We're bigger than this. We're not here. We have to be in this range, right? We have to be here. So we can't reject the null. That sucks. We're here at 13.795. It's not different enough. Not different enough. This means we fail to reject the null, which means it's not significantly different. It means what? It means our set of data right here is not significantly different than this. It doesn't vary as much. We wanted to say to test the claim these weights are far from the population. No, they're about the same. So the standard deviation is the same. All right, so how can we do this with technology? They say stat disk, which I don't like. There's got to be a way to do this. All right, they want to do the confidence interval method. Before we do that, let me see if I can make this work with stat disk. Stats, C stats, T stats, report variance stats. There we go. So there's the variance stats. I'm going to go to one sample with data, which is what we have. We can use this since we have the summary stats. We can do this either way. We want to test this at, was it 0.062? And it's not two-tailed, it's one-tailed. It just has to be what? Less than 0.062. And our critical value, I want to see it. And let's look at this thing. 0.0062. Oh, 0.062, less than 0.062. The sample variance was 0.00. Why is the sample variance 0.0023 when we just got 0.004? I might have typed something in wrong. Oh, because it's using the original one. So let's actually do this with, since we got the data, this could be before I found the mistake. So let's just do the variance stat, one sample with summary. Okay, our variance is 0.04 point, sorry, 0.0413. Okay. Our sample size is 24. Okay. We want to see the hypothesis test for 0.062 and sorry, 0.062. And this one we just want to be what? We want to be less than 0.062. Let's show the critical value. Let's compute this thing. Nice. This is perfect. I think it's because I have that 1.6 in there, something crazy. I don't know, it looks right. I'll see where I messed up, but this is perfect. I'll obviously try it again. Our critical point says 13.0905. Yeah, here's our critical point, 13.09. Our chi-squared statistic should be, oh no, our chi-squared stat is off. It says 13.975. Okay, well, StatCrunch is giving me misinformation, so I'll have to figure out what's wrong with that. Let's keep going. Yeah, it's saying our test statistics are wrong, so I might as well just try this one more time because we already know that we should get a 13.975 for this. So let me try this in StatCrunch one more time. They look identical. Maybe the variance I'm doing is off. Oh, I already see the mistake. What's the mistake? This says they want the variance. Where I was putting in what? The standard deviation. So I just have to change this to this value. The formula is just for variance, but we were using standard deviation. So this is the value I have to put in. And then so my HO using the technology, it's good when I find my mistakes. All right, so it's 0.041341. And my HA has the variance is less than 0.041341. Let's see if this works. All right. 0.041341. This has to be less than that. Show critical value. Compute. Critical chi-square is 13.09. Nice. Chi-square test that is gonna be different. It's gonna be different. So this is just saying that our variance is different. We can't use StatCrunch for it. We can't use StatCrunch and get the same exact answers as these because we found this based on the standard deviation, and this only does it with the variance. Is there one for this? So it's saying that the variance is significant, but we found that the standard deviation was not significant. Whew, exciting. All right, let's keep going with the book then. I guess that's why they told us not to do it. So in the book, we got it right. Our test statistics here doesn't fall outside the range. So guess what? There's not a significant difference. All right, let's try this thing with the confidence interval method and keep going. Let me move my floating head. All right, so here we go. Example 2 using confidence intervals. That sucks. We can't do it with technology. Okay, so repeat the hypothesis test in sample 1 by constructing a suitable confidence interval. First, we be careful to correct this collect because our hypothesis is why is it left tail? Because we want less. That's why we want it over here because we want less than that value. And the significance 0.05, we should use a confidence interval of 90%. Okay, so our CI, our confidence interval, we want to be 90% sure of what is happening. So I guess we have to find the error. All right, using methods described in 7-3, we can use sample data, list in example 1 to construct a 90% confidence interval. We will use n is 24, that is our sample. How they get x chi-squared left and chi-squared right. Okay, so here it is. This is how we get the chi-squared left. Well, we have to first figure out how to get the chi-squared left and the chi-squared right to get these values, which we will get. So they say we use whatever happened in section 7-3. So we're going back in time. There's our chi-squared formula. Does it match? Oh, yeah, it matches. All right, let's get the left and the right. This is what we need. We can't use this formula, so we actually have to find them. All right, so finding the critical value with a sample of 2022. Table A-4 gives us these two values. And then to find error, we use this formula. Okay, so in order to get the values, we have to look at the table for 90%. So we used 21 to the left and 21 to the right to get those two values. We're going to be on 90% here, and our degrees of freedom is 23. So we actually just have to use the table. Now, I know we used I know that there was a way to just do this on I thought we were able to get this on StatCrunch. But am I going to argue with it? No. Let's try to use the table first. So table A-4. Let's see what's going on. Here's table A-4. We want it at 90% cool on one side, and we want it at 10% on the other side. So I believe we're going to be looking at these two, because this is 90% and this is 10%. I believe that's what we have to see. All right, so I think it's going to be between these two. But let's find out together. So to the left, so if we're on 23, one of these values is 13.2007 and the other one's 14.848. Let me just open up this so I have a second one so I can go back and forth. All right, so let's go and look at it. We are in hypothesis testing. 8-4. So what values were they able to come up with for this one? So we got all of these right. We're here. Okay, so they say one to the left. So they say our chi-square to the left is going to be 13.091. And to the right, it's going to be 35 point 172. 13.091. And the 35.172 is all the way over here. So this is this one, right? So that's your, so they're going 95% for 23. Okay. And then they're going 0.05. Why does that make sense? Oh, it does make sense because if we subtract the two, it's 90% in the middle. Oh, okay, that makes total sense. All right, so this is 95% and this is 5%. So between the two, if we subtract them, then we're gonna get a 90% confidence interval. And why should we be working with 95%? That's because that's the main value we started with. So this is between 95 and 5. That's 13.091, which we got before. And that's the 35. So that's over here. This is 35.172. That's how they got the values for the chart. Now I remember getting these on StatCrunch. So I'm gonna just show that how to get them on StatCrunch because I hate looking at the table. It always seems to mess me up. So let's go to calculator. There one that says chi-square. Yeah, so calculator chi-square. Sweet. I knew there'd be. Okay, so if we're talking degrees of freedom of 20, yeah, sorry. We're talking degrees of freedom of 23, and we want to be between 5. Oh, sorry. So if we just want to have 90%, right? Here it is. So if we want 90%, look, there's the 13.09, there's the 35.17. I knew it would give us these values. So there it is. We could just use StatCrunch to automatically give us those two values based on our degrees of freedom. All right, so let's do the problem. We want to be 90% confident falls within this range. So all I'm going to do is use the formula. Here's the formula. So the square root of n minus 1 times the variance over chi-squared of the right is less than our standard deviation. And then we have n minus 1 of the variance again. And we just have your chi-squared to the left. This is how we're going to get our values. And all we have to do is plug these in. So, this is 23. You can remember this is 0.04, right? 0.04. They got 0.048. I think that's where my one mistake is. Sample standard deviation is 0.048 is what I got. I think I just wrote it wrong. I think. Yeah, 0.048. So here we go. 23 times 0.048. Oh, that looks really ugly. Over chi-squared to the right, which is 35.172. And by doing this, we're turning this into a standardized value, so we can use the standard deviation. That's where the square root comes in. So again, 23 times 0.048 divided by the left value, which is going to be the 13.091. So as long as I get these two, I should be good to go. Why don't we just use this? Because we have all the values here. So I'm going to do equals square root parentheses. It's going to be 23 times, I need double parentheses. Oops. 23 times B12 23 times the 0.048 B2. And I just have to divide this by the value we got from the chart, so 35.172. And parentheses, we're good. So here's the first one. 0.1. We should use 3 significant figures. Well, we should use the amount that were in the original. I like using one more than in the original. The original has 3. So we can use 4. So 1771 or 1772. And then all I have to do is change the bottom for this side. I just have to make 13.091. Which is 0.2905. Probably they want it the same though. So most likely your answer is going to be 0.177 is less than the standard deviation of 0.291. This means we are 90% sure that the standard deviation of this data set will fall between these values. So let's see what it says. They got 0.03883 and 0.06063. They wanted the variance. Oh, okay, because in the form I didn't put the variance in. So this is the standard deviation, but we want the variance. So we have to square this number. Sorry for the mistakes. We're human. So basically, we're using the 0.02 instead. So instead of B2, we're using B3. Just got to change this to B3. So there's the 0.064. And here's the other one. It's right here. 35.172. And here we go, 0.00. Sorry, I'm a big liar. 0.039. All right, now it should be right. Let's look at it. 0.03883, 0.0635 G grams. With this confident interval, we cannot support the claim that this, because the value of 0.062 is contained in the confidence interval. We wanted to say that this was different. This 0.0, go back to the original. We wanted to claim that this 0.062 was different. However, 0.062 falls neatly within our range. So guess what? We fail to reject the null. Sorry for the mistakes. I haven't done these before with this value, so. But guess what? As long as we're getting the right values at the end, that's okay. All right. Sweet. There's a way to do it on StatCrunch. Because it's not symmetric, p-values in two-tailed tests are extremely difficult to find. A common procedure in two-tailed hypothesis tests by doubling the tail areas. Okay, we did that. Because chi-squared, it becomes more symmetric the larger sample. It's better for larger sizes. Okay. We're not going to do these where it's not normal. What? All right, let's see what it says for StatCrunch. So they're telling us to do what we just did with variance stats. However, for ours, we needed standard deviations. I'm going to try one more time. So here's our data. Data, stat, variance statistics, one sample with data, variables. It doesn't matter which one we have. Now it's asking us for this, which is the variance, but we're not testing for variance. We're testing for standard deviation. So I honestly don't think we can do it unless we actually have. We can't test this hypothesis that they had us do with the stats because we are testing here for a standard deviation. However, they want us to test for a what? For a variance instead. This one only tests for variance, so we can't actually use StatCrunch for this problem. Isn't that exciting? I'm going to see if I can do it on Excel because I might as well try to do this value on Excel. So we have our data, right? Let's see if I can make this happen. All right, so I'm going to go to data. Got to move my floating head. I go to data, and I'm going to go to what? Data analysis. All right, well, that did nothing. I'm going to try it again. Just data, data analysis. Okay, here we go. I could do ANOVAs. I can do correlations. I can make histograms. We do z-test, t-test, 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 sampling regression, rank, histogram. Nothing says chi-square. Okay, let's look at what the book said. The book says click on the Excel stat in the ribbon and then click parametrics test. Excel stat tab in the ribbon. File. All right, well, I don't have that Excel stat tab, so let's see what other options we have. Find chi-square in Excel. The chi-square dot test function. I like it. Let's see what we can do with this. All right. Returns the left tail. That's what we wanted. We didn't want right tail, I believe. We want the left tail. Okay, so chi-square dot distribution parentheses. So we need our x. I believe this is our sample. Our degrees of freedom is 23. Let's go with true. Let's see what happens. No. So equals chi-square dot test. The actual range is this. And we need an expected range. Okay, that's when we have two sets though. What a shame. I think I have it in mind, so I'm just gonna do one more thing before we start doing the problems. Obviously, we could do it by hand, but I want us to be able to use the calculators and stuff, you know. We might as well be able to try to do this with the calculator just in case they give us one with a standard deviation instead of a variance. If they give you a variance, it's super easy. So let's see the one that I made. Let's go to chi-square. Which example did I use? T-test, chi-square test. Total number of observations, the test statistic, get the critical value. Okay, that's fine. But they don't have one with the calculator, you know? That's SPSS. All right, well, we could do it by hand. I was hoping one of these pieces that I have would help us out, you know? Observe minus expected or expected. Yeah, that's how I've always done it. All right. That's okay. That is quite all right. So let's do the questions. I'll make it really easy for you. Let's just jump to the homework. It's because all these tests can be used in different ways. So here's 8.4. Only have 1, 8, 10, and 13 to try. So let's do them. None of these are going to be too hard. Here's number 1. Number 1 says assume the standard deviation. Okay, so this is our standard deviation is 0.04 and our whistleblower the weights manufactured new products designed to decrease the standard. So this is that's our null hypothesis. We want to decrease this for the alternative hypothesis. So we want to see if this standard deviation is going to be less than 0.04. The sample has these summary statistics. Oh, they give them to us? That's nice. So the summary statistics, so we don't actually have to do the table. So N is 16. Our sample mean is 8.06576. And our sample standard deviation is 0.02176. So we need what? We need this squared How does the norm? Oh, we have to first see if this is normal distribution. So we still have to type this in. So here we go. Let's go to StatCrunch, start typing them in. I was going to just do everything else, but we got to type these in. So we got 8.0652, 8.0730, 8.05, 8.0548, 8.0548, 8.1084, 8.0754, 8.0678, 8.0545, 8.008, 8.0334, 8.0680, 8.0126, 8.0818, 8.0758, 8.0684, 8.0517, 8.0806. Okay, so 16, let's make sure. 1, 2, 3, 4, 5, 6, 7, 8. Yep, it's 16. So the first thing I need to do is graph a histogram of this thing. I'm going to start it at 8. And I want these to be 0.02 each. Oh, let's see how this looks. It looks pretty normal. It's a little bit shifted, but that's pretty normal. If I change this to 0.1, it should be even more normal. It's okay. All right, so now we just need our QQ. Make sure it falls closer to a line. Pretty close. Not perfect, but pretty close. I'll take it. So I think we're good. Now, since we have these values that it gave us, right? It gave us these values. I could also just do stat, summary stats, columns, and just take the first column and hit compute. And it's going to give me the variance for this one for our data. And we have the variance for this one. But we only care about the standard deviation. So because we just care about the standard deviation, I think I have to do this thing by hand again. I know that sounds kind of annoying, but guess what? It's just the way that it happens sometimes. So we have our data. So here's our data right now. I need the sample variance. I need the standard deviation. The thing is, we can't really use the chart because it only does this with variance instead of standard deviation. So we have to do these by hand. So that's what I'm going to do. So here we go. So this one says chi squared equals n minus 1 s squared over this one. Okay, so we already have these values. We should be good to go. Our n was 16, so we know this is 15. Basically our standard deviation, we can see it from here in our StatCrunch. Oops. Well, I can just put it here. So we need this standard deviation for the sample. So let's just go to stats, calculators, Sorry, summary stats columns, we just want variable 3. So we know that the standard deviation, sorry, the variance of this is 0.0065 0.0006587585. All right. That is our variance because it's the standard deviation squared. And now we need the variance of the whole thing. And our problem said that the variance of this thing was, they said a standard deviation was 0.02178. Is that true? 0.02566. Wow. They said that the standard deviation was 0.02176. I really don't like it. 0.02176 squared. All right, well, I might as well just use what they gave us, right? I might as well use what they gave us. So chi-squared is what 15 times 0.00473. All right. And they're also saying 0.00473. So that is the standard deviation. So we have to square this. Sorry, we already squared it. We took the 0.02176 and squared it. All right, and the bottom is, sorry, and the standard deviation is 0.04000. So we have to square that. So that's the standard deviation. So all I have to do, sorry, that's the standard deviation. So if I want the variance, I have to square it. So 0.00, I did it twice. .0016. I believe this is going to be our test statistic. So we're going to do 15 times 0.0000473. I'm going to divide that by 0.0016. So I believe that my chi-squared value is going to be 4.34. Now all I have to do is figure out the value, the critical value that I want. So we can go back to the StatCrunch. I don't know why I didn't get the right values for this, but I'm not going to freak out about it. The calculator for chi-square. And this one was what? 0.05 significant level. So all I have to do is make this what? 0.95. And just change the degrees of, change this to the other way. Oh, oops. There we go. And we just have to change the degrees of freedom to be 15. All right. So when the degrees of freedom are 15, this value is 3.94. See how this value is 3.94? Here's 3.94. Well, we got 4.34, which is in here, which means we failed to reject, which means we reject the null hypothesis. It says it's different. Reject the null, which in our case is telling us that these coin weights are different. They're different enough. These coin weights vary more than 0.04. They vary more than 0.04 for their standard deviation. So I'm going to look in the back of the book. Okay, number 8-3. Number 1, it must be a simple random sample. Okay. Oh, sorry, we're 8-4 now. All right, so 8-4 says it must be a simple random sample, and the sample must be normally distributed. The normality hypothesis claims different ways. It was more strict. That's all they wanted to know. Okay, well, I did all this work for nothing. My bad. So number 1, the only things that we have to do, 1, it's got to be normally distributed. And a simple random sample. Cool. And now they say, how is it different for the one about the mean? It's different because if you're working with means, as long as your n is bigger than 30, it does not need to be normal. However, if you're using something with standard deviation or variance, like in a chi-squared test, has to be normal no matter what. That's why it's more strict. All right. What a difficult question one. I don't know why they gave us all that information. All right, let's do number. Okay, the reason why they probably didn't want us to do that is because 8, you could probably use with the computer. That's why they don't want you to do this crazy one by hand. All right, so let's go to 8. So what's the questions for this? In exercise 5 through 16, test the given claim, identify the null, the alternative, the test statistic, the p-value, the critical value. Then state the claim. Assume that it's normal population and it's random sample. So let's go to 8. All right, so we got weights of 30 girls. So this just means right away n is 30, which means our degrees of freedom is what? N minus 1. 30 minus 1 is 29. Beautiful. The standard deviation. So this is our S. Our standard deviation is going to be 829.5 grams. And that means our variance, 829.5 times 829.5. Our variance is giant, 688.070.25. Beautiful. Okay. We're using a 0.01 significance level. And to claim that the birth weight of girls have the standard deviation as the birth weight of boys. Okay, so. And they say the standard deviation for boys, so this is the one we're comparing it to, which is 660.2 grams. So that's for boys. So what's our null hypothesis? Our null hypothesis is what? It's a, sorry, I don't know why I put a mean. But the overall standard deviation for girls is 660.2. And the alternative hypothesis is that it's not equal to 660.2. This is a two-tailed right here. That's all we have to do. Okay, this is all we're getting. I'm gonna do, I think number 5 also, just to do it, you know. I'm gonna do 5 first. So you can see 5 done all the way. All right, so simple random sample of 153 men, so that's n is 153, and a standard deviation of 11.3 beats, which means that their variance, their sample variance is 127.69. Cool. The normal range is typically given as 60 to 100 beats per minute. The range rule of thumb is applied and the result standard deviation. So our standard deviation here is 100 beats per minute. So then 100 squared. Oh, sorry, it's 10 beats per minute. So this is going to be 100. Okay. What do the results say about the normal range for StatCrunch? All right, so let's do it this way. I guess we can change it. I guess we can just change it by doubling it every time. I don't know why it didn't work before. So I guess we can literally just change it every time. So let's use StatCrunch and just make it happen. Data. Variance, one sample with summary. Okay, so our sample variance is 127.69. I don't know why I didn't think you could do it before. This is 153. Our hypothesis is that ours is going to be 100 and it's not equal to 100. And was it 0.05? It says 0.05, yeah. 0.02, less than 0.05. I want to see the critical value, compute it. Nice. Okay, so if it worked for this one, it should work for all the ones I did previously. So I might as well do this for number 1, the very first one on it, even though it said we didn't have to. And then I'll do it for 5. Oh, I did it. 5, we got the same values. Do we get the same values? I like that it gives us all the pieces too. It gives us the left and the upper. Let's do the one where we found the left and the upper. Let's go back to the very original sample, the very original example. Sorry for being a little all over the place. I just kind of forgot how to do this using the computer. Well, I've never really done this one with the computer before, so let's try this. So let's do options, edit. Okay, so our sample variance is our sample standard deviation was 0.2033, or that means if it's 0.2033, I square that, 0.04133. 0.04133. Our sample size for this one, how many people did we have? 24. And we were testing this against 0.062. And we just had to be what? Less than that value. So I got the critical chi-square of 13.095. But we get 15.332 when I do it. I don't know why. That's so weird that it's off. All right. Well, I'm not going to freak out about it. Let's go right to the one that we just did. It was 5. So So our sample variance was 127.69. Our sample size was 153. We're testing this against a 100. And I want to see the critical value compute. Okay, so here's all the data. And let's look at the answer. All right, so the null hypothesis is that this is going to be equal to 10. The alternative hypothesis is that it's going to be not equal to 10, which totally makes sense. Our chi-squared statistic here says 195.172. And it says our p-value is 0.02. Here it says our chi-squared value is 194. And our p-value is 0.02. To warrant the rejection of the claim that men have a standard deviation equal to 10 beats per minute below. But I don't like the fact that these are using just standard deviations using variances when we want to be using standard deviations. I don't like that at all. But that's how it says we have to do it. Our values look different than the ones on StatCrunch, which is kind of blowing my mind. Sample variance is 128. This one says 127.69. So it says 11.3. I do 11.3 times 11.3 and see what it gives me. It's different. The degrees of freedom are the same. The chi-squared test is off 195 to 194. The p-value is off. Okay, so we know this is the formula, right? This is the formula for the chi-square test. So we have now 153. Sorry, 152 the degrees of freedom. Now I need my sample variance. And they're saying that the sample variance is 11.3 times 11.3. So that's what I'm going to do. Okay. And we also need that value on the bottom. And they say that so we need to get that chi-squared value for 153. N minus 1 over S squared over stim. Okay. All right, so here it is. This should be the value. Let's see who was actually right. 194.008. 194.088. That's what it is. How'd the book get something different? Well, this is right. I don't know how the book messed it up, but I guess the book is bound to make mistakes sometimes. So let's go to stat calculator chi-square. And we want this to be our degrees of freedom of 153. And we want this and we're at 0.05. So theirs is 125.0478. Ours is saying it's between these two values, the lower and the upper. Oh, because it's not equal to this, so I guess I have to go between. I have to go between for 95%. And it's between 120 and 189. And here's 119 and 188. That's weird. Is it because we have to half it for each? No. All right. Well, they say the stat statistic is 195.172. I highly disagree with this. I got 194.088. So the fact that I'm getting these a little off is worrying me. So let's try a brand new problem. Let's try number 7 and see what happens. In example 5, 8-3 involved a test to claim that humans' body temperatures with a mean. Okay, so our sample mean is 98.6. Sample of 126, so our N is 106, which makes our degrees of freedom equal to 105. Has a standard deviation of what? 0.62. That means the variance is going to be 0.62 squared. Point 3844. Okay. Oops. Okay. The sample, the conclusion in the example would change if the sample standard deviation was 2.08 or greater. So use 0.01 significance, so 0.01 significance to claim that the sample 106 is less than this. Okay, so we know that we want our standard deviation. So this is our null hypothesis is equal to 2.08. And then our alternative hypothesis is that we want this to be what? Less than 2.08. What does this tell us about the validity of sample 5? Okay, so we have this. So we want a standard deviation of 0.62, but this says it's 2.08. Kind of wild, right? Kind of wild just in general. So my null and my alternative is right. Let's see if we can get the chi-squared statistic to be right. So the chi-squared formula basically says for this statistic, n-1 times s squared over what? So I have to square this. So this squared is 2.08 squared. $4.324. So this is what I have so far. I have my chi-squared is equal to 105 times 0.3844 all over 4.3264. 105 times 0.3844 all divided by 4.3264. So I got 9.32 or 9.33. That's my chi-squared. Let's see what we should have got. Yeah, that's the answer. Okay. Well, it's working this time. I don't know what errors I was making before. This was 7. And now we need the p-value. We got to get the critical value from the table. Or we could get the critical value from this. So we want it to be less than, and we want it 0.01. So all I have to do is make this 0.99. I just have to change this to be what? Standard 0.99 with the degrees of freedom of 105. We went the other way. Oh, sorry. So if we do that, so I got 74. So I know that this is going to be what? We want anything less than 74.25 because that's 74. We want less than that. And what did we get? Our chi-squared value is 9. So we're in the range. I think we're good actually. This is 74. We ended up with 9. We should be good to go. Yeah, so we can reject the null. This is significantly less. Okay. I don't know why it took me so long to get one right. I'm sorry about that. All right, we could jump into all the homework problems. So that was 1. I'm going to do 8, 10, and 13. Cool. Here's 8. I don't know why it took me so long to get it. Should we see it on the chart just to see? Options, edit. You know that the sample variance here was what? 0.3844. The sample size is 106. The hypothesis testing. We were testing I still think you can't do it because this is different. That's why I think it is, because we have to take 2.08 and times it by itself to get the 4.3264. This is why I think it's different. So I don't think we can just be like, let's just square it. I think something happens with the test, and that's what makes it different. But I'm still going to do this. We want this to be 0.01 now. Compute. It says it's significantly different. Our chi-square critical was 74.25. Beautiful. Our stat was 9.33, and everything worked out. Okay, so I don't know. Number 7 totally works. Every piece of it works. It says it's significant. This p-value is obviously less than 0.01. We're good to go. You can use both for this. I don't know where my errors were before, but at least I'm getting them right now. So let's do 7. We'll do 8, 10, 13. All right. What does 8 look like? 8. All right. So we have a sample. So N is 30 girls. The standard deviation is 829.5. We're using 0.01 significance. If that's the standard deviation, we need to get the variance. So I have to square that. I'm just going to use the computer. Considering it works now. I don't know why it didn't work before, but guess what? I am not arguing in the least because it works now. So 829.5 times 829.5. So this is going to be 688.070.25. Cool. And the standard deviation for boys, they say it's going to be 660.2. So to get the variance of this, all I have to do is square that. 660.2 times 660.2. 435,864.04. All right, so for 8, our null hypothesis is that this for girls is going to be equal to 660.2, and our alternative hypothesis for girls is just going to not equal to 660.2. So let's go to this one. I'm going to do options. I'm going to edit it. My sample variance 688,070.25. And I'll write in the announcements to just skip all the way to 7 because that's the first time it actually starts working. We only got 30 girls here. We're doing this hypothesis test. So squared is 435,864.04. This is two-tailed, so it's not equal to it, and the significance is 0.01. Compute it. It's not less than 0.01. It's not, so it's close, but it doesn't work. So I'm going to reject this. So our chi-squared value is 45.78. And our test, oh, I didn't put the test statistic. No, I did. Oh, why does it have both? Because it has to fall within this range. And it does fall within the range. 45.78 does fall between these two values. So we fail to reject the null. Girls are just as heavy as boys. Fail to, sorry, not as heavy. Girls have just as much variance as their weight as boys. So fail to reject null hypothesis. All right, let's do 10. Here's number 10. So we've got n is 37, which means my degrees of freedom is 36. I have a sample mean of 2.49910. Our S is 0.01648, which means our S squared is going to be 0.01648 squared. So 0.000271594. And the sample standard deviation is greater than, so this standard deviation is 0.0100, so I have to square this. I believe it's just going to move one decimal place. 0.01 times 0.01 is 0.0001. Sorry, there's three O's. 1, 2, 3. All right, so our null hypothesis is that this value is going to be what? Equal to 0.01. And our alternative hypothesis is that it's going to be greater than, right? I believe it says greater than. It's greater than. So I'm just going to use the same thing. I'm just going to use the same StatCrunch. I'm not going to do it again. You saw me do it on number 7 and everything matched up. So I'm just going to edit this. So our sample variance is 0.000271594. Our sample size, I believe it was 30. Oh, 37. And we want to be 0.0001, and we want to be greater than that. And we click compute. So our chi-square stat, right? And then we have our critical chi-square. Notice that this is bigger, right, than this one. So this one falls what? It falls within that little piece over to the right. So because our statistic is bigger, because we're going the other direction, because it's got to be bigger. Here, I can show you over here what I mean by that. But basically for 10, you know what we reject the null significantly larger variation. I'll do this one by hand too, just to show you it works. But here we go. We have a degrees of freedom of 36. We know that we want to go the other way. We want to make this what? So this is where they got the 58.61. See, look, 58.61. Perfect. Now, how do they get the chi-square stat? Well, all they did was plug this into the formula. So chi-squared equals what? It just equals your degrees of freedom times the sample variance over the what variance over the population variance. That's all it is. So to get this value, all I have to do is do 36 times my sample variance, which is what? 0.000271. 5.0002715, and the bottom is just going to be 0.0001. This is going to give me the 97. So here we go, 36 times 0.000271. Ta-da! All I have to do is divide this by 0.0001. We should get the 97. There it is, 97.74. 97.74, it is what? Bigger than the critical value of 58. And then we could look here, this is less than 0.01, so we're good to go. All right, 1 to go. And I'll just write on the announcements to skip until I start working on number 7, because that's the first time I got one of these right. All right, the last one's 13. Why is this good? The answer will be in the back. So here's number 13. Here we go. Number 13. Here it is. The SkyTech Avionics Company uses a new production method to manufacture aircraft altimeters. A simple random sample results in errors below. So we're using 0.05. We have data here, which is nice. I like when we get to work with the data. And we want to know a standard deviation greater than 32.2 feet. So our null hypothesis is that our standard deviation is equal to 32.2. Our alternative hypothesis is that this is going to be what? We're going to test if it's better. And what does that mean? I'll let you do the critical thinking yourself, but this is what we have. All right, so these are our values. Do we assume this is normal? Yeah, okay, so we're assuming it's normal. So here's 13. Let's go right to the StatCrunch. Let's drop them in. Negative 42. We have negative 40. I don't know how that happened. Negative 42. 78. Negative 22. Negative 72. Negative 45. 15. 17. 51. Negative 5. Negative 53. Negative 9. Negative 109. Guess that's everything. Okay. So this is what we have, right? This is all we've got to work with. So I could go to data. I can go to proportion stats, one sample with data. All right, so we're on the fourth variable. Stat, variance stats, one sample with data. So I can go to variable 4. We know that we're testing this against 32.2. And we want it to be bigger. We're using 0.05. And we're going to click compute. It is significantly larger. So what does that tell you? We can double check to make sure that this works by doing what? Let's at least check the critical value. This is 0.05, so this should be a 95 right here. And we also need to change our degrees of freedom to. We got, oops, sorry. Looks like we got 12. We got 12. So that's where the 12 comes from. And we've got to be greater than that 12. Oh, sorry. I got to change this to 0.05. So I don't have 19. Oh, degrees of freedom is one less, so that's why it's 11. Sorry. So that's where this 19.67 comes from. Our actual statistic is all the way over here at 930 something. So this is super significantly different. So really think about it, see where it comes from. Those are all the answers I should check. For number 13, standard deviation. They got it's 0.062. Am I looking at the wrong thing? I was looking at the wrong thing. All right, 32.2, correct, bigger than 32.2. Test statistic is 29. All right, they got 19. Our p-value, or this is 19.675. All right, we got this right. The test statistic is still seeming off. They got 19.675. We got 19.675. Well, might as well just do it. you know? So we know what's going to be what. I think it's because it's using this and the other way, and that I think that's still the same error that keeps coming up for the critical value, but let's do it the right way. So 11, all I need is this one, the variance. So calculator. So we got our variance is 2750. And then we want the one for the total. For the total, they're just telling us this total thing. They're just telling us that the total one, the one that we want, is standard deviation 32.2. So all I have to do is take 32.2 and square it. All right, so this is 1036.84. So it's 11 times 2750.0606. We divide this by 1036.84. So we got a chi-square 29.17. And that's what the book got, 29.17. So we could do it by hand and get that this is 29.17. And then we could just look at the critical value here. So for some reason, if you're ever worried about it, you could always do these things by hand. Is 29.17 bigger than 19.675? Of course it is. Ta-da. So I don't know. I'd probably do it by hand every time if it was me. But at least we got the right answers. Reach out if you have questions. Sorry, this one is like forever long, but I messed it up like 4 or 5 times before I started getting them right. And enjoy your day. I'll do the review and like whatever else is in this chapter.